Thank you. Yeah, a lot of my friends came up to me and said, "Are you okay?" It's not the kind of title I thought I would ever have in my life. It's an example of something known as Schenker's theorem, that what you're going to have to work on is always what you feared the most or hated the most. Anyway, thank you very much for allowing me to talk at this wonderful meeting. And I had a lot of trouble deciding what to talk about, and so I'm going to try to have my cake and eat it by talking for just 2 or 3 minutes about the problem that we've all been struggling with, which is also about having our cake and eating it. It's the black hole information problem. Having our cake means that we'd like a smooth horizon, and eating it means that we'd like the information to come out anyway. And we know that it's hard to have both of those things at the same time. I'm really excited about some recent developments, starting with beautiful papers by Pennington and Almeri, Engelhardt, Merolf, and Maxfield in May. All of these people are here. Several of them are going to give talks, and there are wonderful follow-up papers as well that have appeared since that we'll hear about. And so I'll just say a few words to kind of get you warmed up for that. So what happens in these papers, and I'm sorry I can't review them in detail here, is that you do a bulk calculation according to the way Hawking would have done it. Semi-classical evolution, you have a manifestly smooth horizon. Of course, that results in information loss when you do that calculation. Hawking is famous for that result. And then you do this in ADS-CFT, though. So you can then apply the Ryutake-Yanagi prescription to the entire boundary or appropriate boundary systems, and compute the entropy of the boundary with this bulk. And the amazing, well, what you really do is, you use the supercharged versions of Ryutake-Yanagi. And amazingly, you find an answer that's consistent with unitary boundary evolution. This is amazing not because we didn't expect the boundary to be a unitary theory. It's amazing because once you take this step of doing Hawking's calculation in the bulk, it seems like in the bulk you've made an unrecoverable error, and you would no longer expect this to work. So that's, to me, it was immediately really a fascinating result. In particular, the recognition that there's a new quantum extremal surface that dominates after the page time. It's just a very beautiful insight. And there were a few minor questions about this result. Let's see if I can get this to switch. Yes. In particular, there were auxiliary systems that were employed outside of the original space-time, and it wasn't completely clear whether the entanglement wedge of those systems is the complement of the entanglement wedge of the remaining systems. So with Maria Tomasevic, I found a setup in which this is completely unambiguous, and there, you can just apply the usual RT prescription, and you confirm the results that these people found. So I don't think there's any problem with that part of this argument. So then the question becomes, what does this mean? Let's see if I can here. So here's an interpretation that to me currently makes sense. It seems fairly minimal, and we'll learn a lot more in the next talks. Here's how I'm currently thinking about this. So most of these calculations were carried out explicitly in JT gravity in the bulk. The bulk path integral in JT gravity is known to compute an ensemble average. An average over an ensemble of unitary boundary theories. And this was demonstrated by Saad, Schenker, and Stanford and Witten. And this ensemble, in this case, is the SYK model. And it's really fascinating from that point of view that the black hole interior and replica wormholes that we'll hear about in the other talks are essential for this to work. I mean, that's one way of thinking about what these papers showed. You really need the interior in detail. But I'd also like to stress that it seems clear that having an ensemble of theories, having to average over several different unitary theories, means that you're not going to end up with a unitary theory. An ensemble is information loss. The way I would think about it is that, so on the boundary, if I define an in-state, from the bulk point of view, it's an in-state. From the boundary, it's just an initial state. And I evolve it using one member of the ensemble. and then I evolve it again using another member of the ensemble, I'm going to get two different out states. And if I average over all of these out states, well, the average over many pure states is, of course, a mixed state. So information is lost on the boundary if it's really an ensemble that we're considering. And then by the usual ADS-CFT duality, that means that information should also be lost to an asymptotic bulk observer when the black hole is done evaporating. Well, that's actually exactly consistent with what was found in these papers. In these papers, bulk evolution was done a la Hawking, and information should be lost to an outside observer. It's also consistent with the fact that the RT calculation gave you zero entropy, because the RT calculation is really a bulk path integral. And in fact, the papers we'll hear about demonstrate that very explicitly. And well, the bulk path integral is an ensemble average. So the ensemble average of the entropy is zero, since the entropy in every one of these theories is zero, since the outstate in every one of these members of the ensemble will be pure. So that seems to me a minimal interpretation. We can, of course, hope to argue that this will still hold when we insist that the boundary theory is not an ensemble, but is a single unitary theory. And what Maria and I argued is that this comes with a certain cost. In that case, we start having a discrepancy between unitary bulk evolution and the apparent loss of information to a bulk observer in the bulk calculation. And so either we have to accept bulk information loss, which is information loss. It would mean that if we do an experiment in the lab, we're not going to get the information back out. And at the same time, a conflict between the bulk and the boundary according to the usual dictionary. Or else, I think we're going to have to say words that amount to significant bulk non-locality in an asymptotic region. So even though we're doing the calculation a la Hawking, detectors will see a pure state because somehow there are non-local interactions with the black hole interior. That seems to me a very interesting possibility, but in some sense perhaps more radical than some of the approaches like ER equals EPR that we've been thinking about for a few years, in that we're really putting dramatic new physics into an asymptotic region, not a region where we have at least a black hole. I did not coordinate this slide with Tom. Though, like what he said, it might be related. So we'll now come to the actual talk that was advertised. And this is work that I did with Ven Chandrasekaran and Arvind Shabazzi-Moghadam a few months ago, and as well as a follow-up paper where we were joined by Pratik Rath. All of these are students at Berkeley, and Arvind is graduating this year. So to talk about this, I'll have to review some beautiful work by Neda Engelhardt and Aaron Wall on black hole coarse-graining. And here's how it goes. So the question that they asked themselves, actually, let me not distract you with this right now. Sorry. Okay. So the question that they asked is kind of an old question, and it's a very important one. When you have a black hole that was supposedly made from a pure state, then of course you want to say that the fine-grained entropy of that black hole is zero, if you believe in unitarity. And yet we have this idea of Bekenstein-Hawking entropy. The entropy of a black hole is equal to its horizon area. How do we make sense of that? Well, we'd like to make sense of it the same way that we do for other thermodynamic systems. If I only keep some coarse-grained information, then there should be another quantum state which is mixed and whose von Neumann entropy is equal to the area of the black hole, and which otherwise agrees with the coarse-grained information that we kept. Okay, so that's the task. And what Neda and Aaron did was make that task a little bit more precise. Their construction actually does not work for the event horizon. It works quite beautifully for surfaces which might lie on the event horizon or very close to it, called marginally trapped surfaces. Those are surfaces on which the area in the outgoing null direction is locally stationary. So if I deform the surface a little bit in this light-like direction, the area doesn't change, or the classical expansion is zero in this k direction here. Okay, Those are marginally trapped surfaces. In the L direction, it has to be a negative expansion, it has to be contracting. And there are a couple of other conditions that I don't have time to review that caused them to spoil their entire paper by introducing the word minimar. Anyway, let's not talk about that. So the thing that Netta and Aaron decided needed to be fixed in doing this coarse graining is quite sensibly what they call the outer wedge of the surface mu. The outer wedge is what's spatially on the outside. Okay, so neither in the past nor in the future nor on the inside. And they said, well, so what we should do, right, in this situation where you formed a black hole from collapse is find a bulk geometry whose fine-grained entropy is in fact equal to this area over 4gh bar. And the geometry should have the same outer wedge, but otherwise it could be anything we want. Okay. In particular, what you want to show is that it's impossible to find a completion of the outer wedge which has larger fine-grained entropy. Now, several years ago, we would have had no idea how to make sense of these statements. What is the fine-grained entropy of some geometry? But thanks to Ryo Takeyanagi, we now can make sense of this and translate this statement into saying find a bulk geometry such that there exists a Hubeni-Rangamani-Takeyanagi surface X somewhere behind the outer wedge, which has the same area as the surface mu. Prove that you can't find one with larger area. Okay. Of course, here in the original setup with the collapse, there is no, the HRT surface is just trivial, so that returns the information that we have zero entropy. So what we want to do is find a new geometry over here such that the HRT surface has the right area. Okay, and proving that that you can't find one with larger area is fairly simple if you use the null energy condition and the Maximin version of RT that Aaron Wall formulated. So I won't discuss this much. The remaining task is then to show that you can actually saturate. So to show that you can in fact find explicitly a geometry behind the outer wedge that achieves a surface, an HRT surface X with area equal to that of mu. Okay. And how did they do this? It's quite a wonderful construction, I think. So they attach to mu a null hypersurface, shooting out light rays orthogonally to mu to the past and inward. This is called n minus k. And show that you get to do the following things. You get to insist that the expansion of the light rays remains zero. So you're just basically transporting the same cross-section down along the light rays. The shear is exactly zero, so there's no null extrinsic curvature. And then there's another extrinsic curvature quantity which has to remain constant. And this is consistent with the constraint equations of GR if the following components of the stress tensor are zero. So k is this direction here, I is the transverse directions, and L is the other null direction going in like that. In that case, the stress tensor has to be constant and equal to its value at mu. So they argued convincingly that you can in fact find such initial conditions. These are valid initial data. The really hard part was to prove that as you march down along n minus k, eventually you're going to come to a cross-section of n minus k, which has vanishing expansion also in the L direction. That's what we're looking for. That's an extremal surface. Right? That's the difference between marginally trapped and extremal, or what should really be called stationary, that also the other null direction has zero expansion. So that was quite a non-trivial proof. Then they complete their construction with a CPT conjugation, a little bit related to what Tom talked about. And I won't talk about that very much. What I want to focus on is how can we go further? How can we expand this work? There are some limitations here. We think that more fundamentally, the entropy of the quantum gravity theory, in this case the CFT, the von Neumann entropy in such a theory is going to correspond not to the area of surfaces in the bulk, but to the generalized entropy of surfaces in the bulk, the area plus the von Neumann entropy in the entanglement wedge. So area plus von Neumann entropy of quantum fields. And if we want to generalize our construction to reflect this, what we're going to want to do is hold fixed not just the classical data in the outer wedge and the geometry, but really the quantum state of the quantum fields in the outer wedge. Another limitation, which is of course natural given the setting that they studied, is that they relied on the null energy condition, that TKK is greater than or equal to 0, and that is known to be false in quantum field theory. You can easily violate it. So we need something that's resilient against that because the construction relied on the neck. Okay, so that gets me to the work from a few months ago with Arvin and Ven on quantum black hole coarse graining. Now, of course, secretly our agenda was a different one. We didn't just try to, add some details to what Neda and Aaron had done, though that was, I think, also an interesting purpose. But we'd seen in the past few years several occasions where we learned a lot by taking a purely classical GR statement, such as, for example, the focusing theorem, which relies on the null energy condition, and conjecturing a semi-classical statement, a kind of quantum gravity statement, which is supposed to remain true even when the null energy condition is violated, usually by replacing the area with the generalized entropy in the right ways. In that case, it was the quantum focusing conjecture. The reason that that's an interesting thing to do is that it turns out we can learn new things about quantum field theory by taking clever limits of this quantum gravity hypothesis that we make. And from the quantum focusing conjecture, we learned about the quantum null energy condition, lower bound on the stress tensor, that has since been proven in quantum field theory quite laboriously. So this is clearly a good way to discover new things about quantum field theory that you can then go and check if they're really true. So that was the real agenda here. So what we did was almost mind-numbingly straightforward in terms of just stealing everything that Neda and Aaron had done and saying the appropriate quantum analog should be true. We can't prove it, of course. At the semi-classical level, it's going to be a conjecture. So the conjecture we made is that, first of all, instead of starting with a classically marginally trapped surface, or minimar, we need a quantum minimar surface, mu, meaning that we replace the condition that the condition that the area be stationary under shape deformations in the k direction is replaced by demanding that the generalized entropy outside of mu should be stationary under variations in the k direction. Okay, that's pretty straightforward. The quantity that measures this is called the quantum expansion. It's the variation of the generalized entropy with respect to these shape deformations. Think of V of y as specifying where my surface sits along these light rays that go in the k direction, where y is the transverse coordinate. Okay. So we're going to start with those surfaces instead and try to coarse grain for those surfaces. All right. So then what we conjectured is that things should work as similar as possible under the circumstances to what Neda and Aaron did. We should again be able to find a geometry with a quantum extremal surface x and quantum state rho x. But now we have to make some more demands. We don't just want the outer wedge to be fixed in the classical sense. We want the state, the quantum state in the outer wedge, to always be the same. So we want a quantum state rho x outside of x, such that when you restrict it to the outer wedge, you get back the original state in the outer wedge. And the analog of the area of x being equal to the area of mu is, of course, now that we demand that the generalized entropy outside of x be the same as the generalized entropy outside of mu. Okay. And again, you want to show that you can't find any completion of the outer wedge with larger generalized entropy. That part is actually, again, fairly easy to show if you believe in the quantum focusing conjecture. So that follows from the quantum focusing conjecture the same way that the null energy condition implied that statement for the area in the classical case. But we weren't done copying everything that Neda and Aaron did. We wanted it to work really in exactly the same way. So we wanted this quantum extremal surface x, notice it's now a quantum extremal surface, not a classical extremal surface, of course, to lie, again, on a null hypersurface that you shoot down from mu. n minus k. And we wanted this null hypersurface to be, again, completely stationary in the same sense that it was for Netta and Aaron, meaning that you want both the classical extrinsic curvature quantities to vanish or be appropriately constant, and the quantum expansion to vanish, meaning that you also need it to be true, and this is quite a remarkable thing to demand of a quantum state, that the entropy of the quantum state outside of mu is the same as the von Neumann entropy of the quantum state outside of any cut that I define on n minus k. So I make the region larger, but I want it to be true that the quantum state restricted to whatever the larger region is has the same von Neumann entropy as the quantum state in the outer wedge. Okay. Then, of course, the conditions on the stress tensor go along for the right, except that we're now writing down expectation values. And the entire purpose of this exercise is to say we can make a prediction here. Such a quantum state, if this conjecture is right, should exist. It's a weird kind of quantum state. In fact, there's something else that quantum state must have. This quantum state must have a shock, a stress tensor shock, right here at mu. How do we know that? Well, that follows from what we've already demanded. So we demanded that the classical expansion on n minus k should vanish, so that it's really a stationary null surface. In the classical case, the expansion already vanished at mu, and so this wasn't great news. But in this semi-classical case, all that we know about mu is that the quantum expansion vanishes there, which means the classical expansion in general will not vanish. It'll be equal to minus the functional derivative of the exterior entropy. Okay. So we're saying we're going from having non-zero theta to zero theta instantaneously as you go down into n minus k from mu. Okay. The only way that can happen is if you have a delta function shock in the stress tensor of exactly the right magnitude, sitting right here at this cut. Okay, so the quantum states, in addition to having to satisfy these conditions on the expectation value of the stress tensor and on the properties of the von Neumann entropy outside of cuts being constant, will also have to have this very specific shock at the cut. So let's now ask what this implies for quantum field theory when gravity becomes weak. So we want to take the limit as g Newton goes to 0 and extract some lessons from this conjecture about how quantum black hole coarse graining is going to work. So to take the g Newton goes to 0 limit, we're going to consider a situation where we have small perturbations around a killing horizon. So here's an eternal black hole. Here's its horizon, and we treat the matter perturbatively. Here's the outer wedge. Some arbitrary cut on the horizon is mu. And this just summarizes what I already told you. We now predict, in a sense, that there exist quantum states on this infinite null hypersurface, the killing horizon, that satisfy all of these properties. Okay. Now, before I discuss whether they really exist, let me first stress that this is, in a sense, a stronger claim than the Ant conjecture of Aaron Wall. In other words, it implies the Ant conjecture. If it's true, it implies the Ant conjecture as a special case. The Ant conjecture is the following question. So you have access to some part of a stationary null surface. Aaron was mostly thinking of a null plane in Minkowski space. And you don't know what the remaining semi-infinite region is. And you ask, what is the smallest energy that you could still have in this remaining semi-infinite region? There must be some infimum, since the energy is bounded from below for the global energy. And Aaron showed that the energy has to be at least equal to this quantity. Okay. And the Ant conjecture was the statement that you can find that the infimum is in fact this quantity, so that you can achieve this, that you can saturate this. Okay. This would be immediately implied by the statement that the stress tensor vanishes in this entire region and has a shock of exactly the right value to give you this energy right here at mu. Okay. The Ant conjecture is in turn very strong because it implies the quantum null energy condition. And so this is a relatively powerful set of predictions that you can get out of this quantum black hole coarse graining idea. Now, unfortunately for us, Sayan and Faulkner had already just proven recently the Ant conjecture, and they had in fact constructed explicitly purifications of one side of a null surface that achieve this minimum energy that Aaron conjectured. Okay. What they actually did, though, was something I'll come back to. They considered actually a whole one-parameter families of states and then showed that the property that they wanted is approached as that parameter S goes to infinity. Okay, so they proved this. Well, the next best thing to what we'd wanted to do was then to take their wonderful work and see if just by sheer luck this set of states that they had defined in the S goes to infinity limit also gives us all the other more detailed properties that the quantum black hole coarse graining conjecture predicts some states should have in quantum field theory. We're of course not guaranteed this. It could have been that the states that they found are good enough to show that the Ant conjecture is right, but you need some other states to actually achieve the other properties that we said should exist somewhere in quantum field theory. But it turns out that we got lucky. If you use the Sayan-Faulkner limit state, you find that it also has the other properties that we wanted. In particular, it has exactly the right stress tensor shock at the cut. Okay, so this is a nice quantitative check that it really works. And it also has this weird property that the entropy, the one-sided entropy, is independent of the cut in the completion. Okay, so with this newfound enthusiasm for the one-parameter family of states that Tom and his collaborator found, we decided to think a little bit more about really that whole family and not just about the S goes to infinity limit. Okay, so at this point I'm going to switch over fully to thinking about quantum field theory in Minkowski space, and we're going to be interested in the simplest null hypersurface you can think about, which is the null plane, x equals t or whatever, u equals 0. And so on this plane, of course, if we take a planar cut, then that cut divides the space into the left and right Rindler wedge. More generally, what we can consider is a wiggly cut, described by some function v of the transverse coordinate y, which still divides the space-time Minkowski space into a left and right wedge. It's just not Rindler wedge. It has a funny shaped boundary. And here you see a Cauchy surface of the right wedge. Similarly, there will be one of the left wedge. And separately, the Cauchy developments of this define the wedge. Okay. So now I have to start talking about Connes-Cocycle flow with some trepidation. That's what Sayan and Faulkner actually did to get their family of states. Okay. So here's how it works, I think. So you say you have a global pure state. Let's call it psi. Okay, that's the state you're starting from. And now you're going to generate a bunch of other states. And these states will have the property that they reduce to the same state in the right wedge, but they're different globally. Okay. And so here's what you do. So you have this wonderful thing. By the way, if you're as new to the subject of algebraic quantum field theory as I was, and I highly recommend Edward Witten's wonderful summary of the subject in a recent review. So there you'll find detailed definitions of these operators. Delta prime psi omega is the relative modular operator of the left wedge algebra. Psi is, as I said, is our arbitrary global pure state. Omega here is the vacuum. And then delta omega prime is just the vacuum modular operator, again defined for the left wedge. A non-trivial result of algebraic quantum field theory is that this combination of operators is in the left algebra. Okay. And now we're just going to take it to appropriate powers of is. Okay, and that generates a one-parameter family of states psi. Now, this to me is entirely abstract. And so to get some intuition, let's work our way back to things that are maybe a little bit more physical, depending on how you grew up. So we all know what Rindler energy looks like and what a boost operator looks like, right? It's, if you have a planar cut, you would just integrate over the transverse directions and then along the null direction, the stress tensor weighted by its distance from the cut. Okay, that's the boost generator. And it turns out, so of course this is also the log of the quantum state in one wedge divided by the quantum state reduced to the other wedge. So it's the log of this vacuum modular operator. But it turns out, and this is a more recent result, that this is called the modular Hamiltonian. It takes the same form even when the cut is wiggly. Okay. You can't write it down nicely if you want to try to write it down as an integral over the spatial regions, which you could if you had a planar cut. You can't do that anymore, but if you write it as an integral over the null hypersurface, it looks pretty much the same. You just think of it as basically the boost operators for each null geodesic separately, defined across wherever the cut is on that particular geodesic V of y. Okay. So kinematically it does the same thing. It moves points around on the geodesic. The boost is just a dilation on the geodesic, so it moves points away or closer to the cut. Okay, so that's the intuition that we're going to work with here as we now inspect a property of Connes-Cocycle flow, which you will find in Tom's paper. It's the following statement. First of all, this is kind of clear given what I already told you, that this Connes-Cocycle operator acts only in the left algebra. So clearly on the right I'm going to get the same reduced state, and I'm going to get the same entropy for any cut that I impose on the right. So let me just indicate a cut on the right. So suppose I make a cut here on the null plane, and I ask what is the entropy here. It's going to be the same before and after. Therefore, it's also going to be the same left entropy since I have a pure state globally. Okay. On the left, it gets more interesting. On the left, the following equation holds. What does this equation tell us? If gamma prime is in the left algebra, so it's not some, say, two-point function between a point on the left and the right. It has to be just on the left. Then I can figure out what the expectation value of gamma prime is in the float state by computing the expectation value of the boosted operator gamma prime in the original state, or anti-boosted really. I evaluate gamma prime in the boosted version of the original state. You can put it either way. Boost is in quotation marks here because I want to remind you that this is not really a boost. It's a boost sort of generator by generator. So you can really think of it as a boost, as a sort of local operation only on the null hypersurface itself. Okay. Moreover, the one-sided entropy of a cut on the left, so now we're going to consider a cut on the left side and ask what is the entropy here, or on the other side. They have to be equal because it's a pure state. This looks like a complicated formula, but it just says that it also transforms under a boost. In other words, if I want to know what the entropy is after I've done the Connes-Cocycle flow with parameter s, all I need to do is take the cut that I'm interested in, dilate it back to the original position of these points using the boost operator, and then look at what the entropy was in the original state for that cut. Okay. So the point of going through these properties is that, to me, what I learned from this after staring at it long enough is that this Connes-Cocycle flow is the next best thing that we have to a half-sided boost in quantum field theory. Classically, of course, you can always consider data and perform a boost only on one side of the Rindler horizon, let's say. But at the level of quantum field theory, you cannot do that. Even the tiniest boost will immediately destroy the vacuum and give you divergent energy density at the cut, because the entanglement structure of the vacuum is just destroyed at every wavelength. Connes-Cocycle flow kind of does that. It boosts all the excitations in the sense that the operators satisfy this equation, but it repairs the vacuum in some sense. So that's the intuition on which the next steps will be based. So what we were interested in is if you did this Connes-Cocycle flow not on any old quantum field theory, but on a quantum field theory that has a gravity dual, what might be the bulk dual to Connes-Cocycle flow on the boundary? Okay. And given the intuition I just gave you, it will not surprise you that our guess was that we have to do a sort of half-sided boost. Again, because it's not really a boost, we called it the left stretch. And it doesn't really have to be on the left, but in our pictures, it's always going to be on the left. The left stretch means, so in the bulk, remember, in the bulk, I just get to do this without having to worry about destroying the vacuum, because I'm interested in doing this to leading order in 1 over n. And so I just can do a classical construction in the bulk. Okay. What am I going to do? Well, I'm going to look at whatever the cut was on the boundary, which divided my boundary null plane into n, little n, k plus and minus. The Connes-Cocycle flow changes things here. Okay. I'm going to look at this cut and find the RT surface, or HRT surface, in the bulk. Notice that the bulk need not be anything like vacuum ADS. Could be a black hole in there or all sorts of stuff. So that's why we need HRT. So I'm going to find this HRT surface, construct the null hypersurface orthogonal to X, the HRT surface. Let's call that nk plus and nk minus. Of course, there's another one, but I want the one that's adjacent to the little n's. Okay, that's obvious what that means. And now, Connes-Cocycle flow, we conjecture, corresponds to, in some sense, stretching nk minus in the way that a boost would stretch data if this was really a planar cut. But we need a prescription that makes sense of that statement when this is a non-planar cut in a completely general geometry. So let's say what that prescription is. So this is, again, a classical construction in GR. This, in turn, we could iterate everything I said and try to find a semi-classical version of this. I'm just going to discuss the classical construction. Take any null hypersurface in any space-time. Identify a surface X. And now we're going to do the following thing. So if X has 0 expansion in the k direction, so it's a marginally trapped surface in some sense, then we get to cut the null hypersurface at X. The next thing we'll do is whatever the affine parameter we had chosen for the original null hypersurface, on every geodesic, we're going to rescale it by the same factor e to the 2 pi s, but only on the left side. Okay, that's what's shown here. So I haven't done anything physical yet. There's some system here. I'm just using a different coordinate system. Okay. And then we glue it back together at X. And now the key step is that we treat the new affine parameter really as an affine parameter, although it's not. In other words, for it to be an affine parameter, something really has to change physically. Okay. I'm running out of cake. I'm also running out of time?
Yeah, you're out of time.
I'm out of time. Okay, I'm also done, almost. So let me just finish. Okay, so this is a way of generating new initial data, and it's really a family of new initial data from old initial data. At a minimum, we need X to have 0 expansion. What this does is, in general, it changes the left wedge, but not the right. It changes the left wedge because the expansion in the other null direction is governed by gravitational constraint equations, which will make it be physically inequivalent compared to the original data on the left. And of course, the global state then changes if you evolve it. If X is extremal, however, this does not happen. And in our case, X is going to be extremal because it's the HRT surface. Right? In that case, the left wedge and the right wedge separately just receive a diffeomorphism under this construction, and so are physically equivalent modulo the way that the boundary in ADS might be acting on them, but at this bulk level they're equivalent. Nevertheless, of course, there's still the future and the past of the surface X which will be different. So the global state will be different after the left stretch, even then. Okay, so I think given what I've said, it may already be quite clear that this construction is going to satisfy the conditions that we imposed. Let me review them here. The left expectation values transform just under a boost, and the one-sided entropy will be the same, simply because what this just says is that we can evaluate these things holographically in the original geometry. And since we haven't changed the geometry, we'll get the right answer. Okay. The quantitative test is, again, the shock, and that's the long, tedious calculation that I will spare you. But we know already that for S goes to infinity, we have a shock of this size at the cut. This is on the boundary. Here's the finite S generalization of that, which is also found in Tom's paper, or can be extracted from it. So what we needed to show is that under a bulk left stretch, using the holographic dictionary, you reproduce this shock at the cut on the boundary. And that turns out to be true. So what happens is that there's a Weil tensor shock that's introduced by the jump in the shear that you will cause by stretching the hypersurface on the left but not on the right. That changes the shear very suddenly. That requires a Weil tensor that goes out to the boundary, and that has exactly the right size to be dual to the boundary stress tensor that was predicted by the Connes-Cocycle flow. And with that, I'll take some questions. Thank you.